Welcome to the NST lectures on modular architectures. My name is Herwig Mannaert, and in this second part we are going to dive into the design directives, the well-known design directives for modular architectures, and explain how they can be grounded in combinatorics. We have seen in the first part that modular design and production modularity is a cornerstone of modern engineering, and that modular design needs to encompass the manufacturing process as well, not just the design, because we face the essence of modularity during the process of producing, creating, manufacturing the artifact. Now, having a modular design and production allows us to grow the number of product variants much faster than the number of variants of the individual modules. However, changing or adding a new module variant or version may cause impacts on other modules, including all their variants and versions. Now, these impacts can propagate or ripple throughout the modular structure and may grow much faster than the number of the individual module variants. So it is quite powerful, but also a bit dangerous. Now, modular design, we have also seen, and production is applicable to all kinds of artifacts, physical artifacts, but not even limited to physical artifacts. We have given the example of the chair production, but software program, car assembly, but also composing a study program or a business process flow, or even artifacts like a cough syrup, where the ingredients are the modules and not physical parts. But how do we design the structure? How do we define the modules? How do we specify the modules and architect the structure? Now, there are some well-known design guidelines or directives: low coupling and high cohesion. Everybody knows this. The problem, however, is how to do this. So let us dig into the rationale. Let us dig why we want low coupling and high cohesion. And maybe then we better understand how to do it. So we study why we need it and try to capture the mechanisms, because we believe that is the way to fully grasp and understand how to do it. So coming back, for instance, the legs of a chair. We said modularity, we need it for complexity reduction, but also, well, why do we separate the modules and want high cohesion? Well, we want to avoid the duplication, for instance, of the leg manufacturing. We want to avoid the duplication of a desired or mandatory change. We want to enable changes and optimizations to the unit. We want to, be able to change, to optimize it and support multiple variants. That's basically why we want to separate the legs of a chair or something else into a separate module. Low coupling. Why do we want low coupling? Well, we want to limit the dependencies of the other parts. We want to avoid having impacts of changes in the other modules. We want to avoid a new variant impacting the other modules, impacting the integration at manufacturing time. Another example in the software sector, a logger in a program, a simple logger. Why do we want to separate it? Why do we want high cohesion? Well, we want to avoid duplication of the logging code by separating into a separate module. We want to avoid the duplication of a desired or mandatory change. If we avoid duplication, we avoid duplicating a change. We want to enable changes and optimizations at a specific single place. We want to enable support for multiple variants. And why do we want low coupling? Well, we want to limit the dependencies of the program. We want to avoid the impact of change to the logger to the entire program. We want to avoid impacting of a new variant having an impact on the entire program. That's why we want low coupling. Avoid impact on the integration at build deploy time, not just at source coding time, but also at building, deploying with another kind of library could also have impacts. So why do we want to have low coupling? We want to have low coupling to avoid that changes ripple through the entire structure. Now, so let us look at the combinatorics of modular architecture. First, it's about separating modules. We want to separate modules, high cohesion, because we do not want duplication. That's basically the main reason. And so we talk about the exponential variation gains that we could have by separating modules into highly cohesive separate modules. If we create a system or process, because we have explained that the modularity can only be viewed and seen and studied in detail and in depth if we look at the manufacturing as well, the creation of the system or process, for instance the chair, but we can have many other examples, and we will give during this presentation always the same 6 sample examples. I will not always explain them, I will not always mention them explicitly, but they will be there on the slides. Suppose, for instance, a chair, suppose a software program, a car assembly, composing a study or training program, a business process flow, or a cough syrup production. 6 kind of totally different examples of systems that we could produce or manufacture. And so they give you quite an idea about what the issues are, what the kind of modules are, the issues in the modular structure. Now, if we start producing, manufacturing, making, creating systems, then we see that we get so-called units of work, separate units of work that emerge in such a system. And those units of work that emerge in such a system, they can have multiple variants. Now, for instance, in the chair production, we have seen we get chair parts, we get upholstery, seat, a backrest, and we get multiple variants of it. In a software program, logical units of work arise, emerge, and we can have many computation variants of sending a message, making a computation, encrypting something, etc., etc. And also in all the other examples of those manufacturing, creating, producing artifacts, we see that we can have units of work like the parts in a car, the modules in a course, the tasks or activities in a process flow, the ingredients in a syrup, for instance. So you have these units of work, and different variants emerge for these different units of work. Now we can have, of course, one global module, one global production, manufacturing, program unit. And then we would have multiple variants of every one of these units of work, and they are represented here as, for instance, Unit 1 has K1 variants, Unit 2 K2 variants, etc. until Unit N has Kn variants. Now, the unit version would be the sum of all these variants of versions, and in this case we would have a production, a manufacturing, or a computer program with lots of glue logic. We would have a single chair manufacturing system where all the variants of all the parts could be accommodated, and during the manufacturing, during the process, there would be a selection. We could have a complex program where all variants for all processing units, computation units would be present in the program, and we would have selection logic to select the appropriate version of variant everywhere, and so on for the other examples. That's of course a monolith with lots of glue logic to select, identify the variants of the various units. So another possibility would be that we would have variants for the global model, for the global system, for every combination. So we would have, for instance, for variant 1 of unit 1, variant 2 of unit 2, etc., we would have a specific computer program. We would have a specific manufacturing system for the chair, etc., etc. Now, in this case, yes, we would have the unit versions of all the variants and versions of the units would be the sum of all the variants or versions, but we would have the product of all of these variants. The product would be the total number of production manufacturing units software programs. So we would a hell of a lot of different manufacturing units, each manufacturing a specific combination of all the variants. Each software program instance using a specific combination of all the variants of the computation units. We would therefore have loads of duplications in the variants, because if we would take, for instance, a single variant of unit 1, it would be present in every instance that would use that variant, and that would be the product of all the number of variants of all the other units, which is a huge number. So that's also not ideal. We would have a chair manufacturing unit for every chair type. We would have a dedicated program for every input set of configuration, etc., etc. So what is an alternative? The alternative would be, of course, that we would have chair parts, variants of parts, and that we would have separate modules for every part or every unit of work. So we would have for unit 1 a module 1, we would have for unit 2 a module 2, we would have etc., etc., and for unit N we would have a module N. Now it's important to note the difference, of course. They are still units of work, but now such a unit of work is properly encapsulated and can be properly used outside that single system. It gets a life of its own and it can be used on its own, which it couldn't be. Now we can have a separate leg production. Before, it was only an implicit part of the production of the chair. Now we can have a separate module for a certain computation. Before, it was just a piece of code within a larger software program, etc. Now, of course, the units of work would have different variants, so the modules would also have different variants. That remains. K1 variants, K2 variants for module 2, Kn variants for module N, for instance. So the total number of module versions is now the sum of all these number of versions or variants. But for the system variant, we can have the product of all these versions of variants. Now, I use a bit the term variant and version as a bit of the same notion, but in fact the variants are typically different instances that occur at the same time and the versions over time, but it's not kind of that absolute, but I kind of use them together, but in general the variants are at the same time, the versions over time. So what we see here, for instance, for every chair part, for every unit of work, a set of modules, for every computation we have a set of different functions or methods or classes. For every car part we have a number of set, etc. So if we now look at this situation compared with the previous situation where we did not have separate modules, we had the sum of all the versions or variants as a total number of unit versions, and we still have it the same number as the total number of module versions. However, in the first case, on the left, we would have the product of all these versions or variants of all these units as the total number of modules. In the second option on the right, we have that product as the possible number of system variants that we could have, but we don't have them, we just enable them. We make it possible that you could have all these variants as combinations of the different modules. So what you basically have is an exponential variation gain, because you only have to create and maintain the sum of the various versions and variants, and possibly you can have the product of all the versions and variants as possible systems, as possible actual artifacts that you couldn't have in the first case. Of course, provided that you have a hierarchical aggregation system. Now, if we look at an example of software frameworks, if you have web applications, information systems, multi-tier, and the frameworks are a couple of years, maybe they get a bit outdated, but it's just to give you an example that if you typically have a number of technologies like database, persistency frameworks, transactions, remote controlling, styling, access, if you have a number of technologies, in general, the multiplicity is not that high. You don't have for a single technology or for a single part a very high multiplicity. You see that the multiplicity is typically here 2 or 3, maybe 4. So the multiplicity is not that high. However, the number of units, the number of frameworks, the number of possible modules is indeed pretty high. And that results in quite a difference. So the sum, the number of versions or variants of the modules, the frameworks you need to support is, for instance, 17 in this case. And the product, the number of variants that you can have, is 384. So it is an exponential variation gain you can have. And it is quite an important variation gain, an impressive one, because it's even exponential. And it's not the multiplicity that is that high, but the number of technologies, modules, quite easily grows big. So you have these conceptual exponential variation gains that are enabled by having multiple modules. So we turn to the second part, high cohesion, low coupling. Of course, we have to aggregate the modules as well. The whole point why we did have different units and therefore different modules is that we need them, and we need a whole system, a whole product, a whole artifact, so we need to aggregate it as well. And if we aggregate those modules, then it is about low coupling. Then it is about not propagating impacts of changes. Because then you can have the other side of the coin, the danger of exponential ripple costs instead of exponential variation gains. So suppose you have all these modules, module 1 to n, and they have this number of variants or versions, k1 for module 1, etc., kn for module n. And now suddenly in module 2, for instance, you make a change to a certain variant. You change variant to a variant. But then, suppose that for module 2, the number of connections, the number of links, the number of other modules it is connected to is D2, or DI in general. Then, potentially, by changing a single variant of that module, you can have an impact on all the modules which are connected directly. So basically, the impact you have is you have to sum over all the connected modules, so to DI, and you take the number of versions or variants of these other modules, because all these variants of these connected modules can be impacted. Of course, however, if they can be impacted, it is possible that they need to be changed, and if you change those variants of those connected modules, then they become changed as well, and it is then becomes possible that the impact of change is further propagated to the modules connected to those modules that were connected to the original module. So you had a second order impact where every variant of every module connected to the modules that were connected to the original module where you changed a variant can be impacted. And that's only the second order impact, and there's of course a third and a fourth order, and it can ripple throughout the whole modular structure, and it can even come back to the original module, asking yet again changes to the original module, so you could even have an infinite ripple of propagation of change, theoretically. So while we have the exponential variation gains as a major advantage enabled by having different modules, now of course you can have impacts propagating between and through the modules, and these impacts or ripples have a cost as well, and they are also exponential because it is based on a number of variants connected and it can ripple throughout the structure. So you can have exponential ripple costs. So changing a leg of a chair, it can have an impact on the connection. Changing a version of a certain computation or an encryption or a message can have an impact on the code around it, the code calling it. Changing a car part, etc. Changing a substance in a fever, of a fever ingredient in a cough syrup can have an impact and an interaction and an adverse effect based on the combination with the other ingredients, for instance. Now, of course, we have seen in the first part that this coupling, these impacts, are not always that straightforward. You can have many ways of impacting. You can have, of course, the physical dimensions, the attachments of the legs of a chair, but you could also have impacts through other kinds of properties like the hardness, the corrosiveness, the thermal properties, etc. So in here are some examples of impacts which are not the most straightforward, like a physical interface or connection or attachment, but the hardness, the corrosiveness of a chair leg. In software, for instance, you would need a new underlying library or development kit, like the Java development kit, or the car part would make the cooling liquid too viscous and you could have an impact on something else. You could have an impact on the solubility of an ingredient in a cough syrup. So it's not just possible to have impacts through the obvious interfaces like physical dimensions, attachment points, but through all kinds of properties of the materials, etc. And there are many properties. And you could also have impact based on an aggregation process or in time. For instance, a fever ingredient would need directly pressurization and the other ingredients would not need it. Another type of chair leg would have to be mounted earlier in the manufacturing process than it used to be. A module in software would have an asynchronous request instead of a synchronous, etc., etc. You could have another study module that required a prerequisite. You could also have all kinds of impacts based on all kinds of properties of materials and substances, and also all kinds of impacts on the process in time, on the sequence. So there are many, many, many possible ways of having those impacts. Moreover, the whole point of modules is that you could also use them not only in the original artifact you are creating, but also in a kind of an other artifact, that you could use the leg of the chair in another kind of chair, or for a table, that you could use a computation in a software program, a certain computation, or sending a message in a completely other software program. However, if you reuse that module 2 of the original artifact or system in another artifact of system, let's say as module X, then the same thing could happen impacting the other system, the other artifact, impacting all neighboring modules of the other system or artifact and impacting them in its turn on the other. So you have exponential ripple costs also in all other artifacts or manufacturing processes where you would reuse that module. And remember, reuse is one of the fundamental reasons that we want modules and use modules. And here are some examples: reusing the chair leg in another chair or table, etc. So you can go through it. You can imagine many kinds of reuse. It was the original purpose of modules, and it gets you into more potential trouble with the ripple costs. So basically, the design directives of modular structures or architectures, high cohesion, low coupling, they are basically grounded in combinatorics. You want to unleash through high cohesion, through separation, the exponential variation gains, unleash them. But of course, then you need to master the coupling, because you unleash the exponential variation gains, but you could also unleash the exponential ripple costs between the module, and that would destroy your evolvability. If we look again at low coupling, high cohesion, and we try to reinterpret, as we stated in the Normalized Systems Theory book on page 328, well, basically they're kind of the same underlying mechanisms. The high cohesion is to avoid the intramodular coupling, to avoid the duplication of changes, the duplication of effort, while the low coupling wants to avoid the intermodular coupling, the changes propagating, rippling through to other modules. And it's not only by counting just which modules are connected to which modules. If you look again at the logger, of course, you do want to use and reuse the same logger all over your application. And you could say, well, if we count the number of times the logger is used, it would be an enormous number and it would be an enormous coupling, but that's not bad. It's reuse, it's nice. You don't want to use 100,000 different loggers, you want to use 100,000 times the same logger. But of course, you need to make sure that you don't get ripple effects, that if you change the logger, you don't get a ripple of change to 100,000, 100,000 places. So cohesion is not just about splitting into a sea of modules, it's about also the hierarchical aggregation of the related modules. Now, in addition, and that's very important, you always have in modular structures or architectures, like productions, artifacts, manufacturing, software, cough syrups, chairs, cars, you don't only have the main structure or the main hierarchical structure or dimension, you have other dimensions, other concerns that need to be integrated across the entire hierarchical structure. So for instance, you have a software program and then you need to make it highly robust, secure, access control across the whole structure. Now in software, people typically call this cross-cutting concerns, as these are concerns that cut across the entire structure. It is named and coined based on the architectural composition. In construction, for instance, typical additional concerns are heating, water, electricity. They call their utilities. But in the same way as the cross-cutting concern in software, they cut across the main functional structure. And so you also have, for these other concerns, take into account all other kinds of couplings like weight, vibration, emission constraints of an engine. Now, these concerns like water, electricity, heating, access control, etc., they have their own modular architecture. And that own modular architecture needs to be interconnected with the main hierarchical structure or architecture. And of course, coupling is a very dangerous thing, and it can lead to impacts propagating both between and within the various concerns of dimensions. So here it kind of looks like rooms in a construction. It could be software modules, But when we have such an hierarchical structure, it is basically, first we only see the main structural dimension. It is actually just one dimension. But then you need to add other concerns, other dimensions, like water electricity in construction or access control, persistency, robustness in software. So, or having a coating for all parts of a chair, persistency, access control, electrical power control to all the parts in car assembly, etc., etc., asking for internationalization or case studies in all modules in a program, all these kind of concerns that cut across the functional structure. And so it cuts across the functional structure, so you get additions in the various modules because it cuts across the functional structure. So this concern needs to be addressed across the functional structure in all of these modules. And it is interconnected in the same way. But changing in these other concerns, in these utilities or other concerns, can impact and change the main functional modules. And it can also propagate or ripple from changing then those main functional modules to the connected other functional modules. And so you can have much more impacts of changes rippling through the main functional structure, although the changes originated in the structure of one of the other concern dimensions of the cross-cutting concerns. And so we can have the first potential impact, where we can have impacts in all the various versions or variants of the modules, but we can have potentially second order impact, third order impact, etc., etc. So now it is about time to study these other dimensions, these other cross-cutting concerns, and the interconnection between these other concerns or dimensions with the main functional structure, with the main structural dimension. My name is Herwig Mannaert. You can always email me questions.